Hello everyone. Today I am going to discuss about bipolar junction transistors. So in the first few slides I am going to discuss about the bipolar junction transistor and its structure. Then I will be discussing about the working of bipolar junction transistors, and then after that we will be doing some problems on the circuits of bipolar junction transistors. So as you all know, the transistor consisting of two p-n junctions. So basically two p-n junctions connected back to back. So here we can see there are two types of transistors. One is an NPN transistor, other one is a PNP transistor. In the case of an NPN transistor and two PN junctions, that is N and this N junction is connected with the P junction. Okay, this will form a diode. Again, this P and N junction and part will form another diode. So this is a one NP diode, the another one is a PN diode. So when they are connected together, it will form an NPN transistor. Okay, so a P junction is sandwiched between two N junction, then that is called an NPN transistor. Similarly, for a PNP transistor, you have an N junction between two P side semiconductors, two P semiconductors. Okay, so it will form a PNP transistors. So there are two types of transistors, NPN and PNP, depending upon the structure of the transistor. Now, again, we know there are three types of three terminals are existing in the case of a transistor: an emitter, base, and a collector. So, emitter, this forms the first junction will form first lead is called emitter. Other one is called the middle one is called the base, and the last section is called the collector junction. So what is the difference between these three junctions, three regions? So emitter region is a heavily doped region. Emitter is heavily doped, okay, and base is very lightly doped, okay, and collector is moderately doped, okay, moderately doped. So why it is why the doping levels are in such a way that emitter is heavily doped, base is slightly doped, and collector is moderately doped? Because the reason for this is that emitter region is always emitting charge carriers, either electrons or holes. So that is why it is heavily doped. It is actually the source which generate more number of electrons or holes. So that is emitter is heavily doped, and whatever we transmitted from emitter to the transistor, it should reach the collector without any loss of its strength. So in order to avoid any loss, we are keeping base region lightly doped. If the doping level in base is high, there may be a recombination occurring in base region. In order to avoid this recombination, we are keeping base region lightly doped, and collector should be moderately doped in such a way that it can receive whatever the electron coming from emitter through base. So that is the idea of keeping different doping levels in three different sections. And about the size, the size of the collector is usually very large compared to other two, and base is very lightly uh, the width is very light, and the emitter region is having a size between the base and the collector. So these are the properties of three terminals of a transistor. Now, see, I have told there are two types of diodes. We can consider a PN junction as a combination of two PN junctions. So it is, you can assume to be a two diodes. So first diode is called the emitter. The diode which is forming between the emitter and the base is called emitter base diode, and the or it is simply called the emitter diode. And the for the proper operation of a transistor, the emitter region should be always forward biased, that is junction between emitter and the base should be always forward biased, and the other diode, collector diode, should be always reverse biased. So base emitter to base junction should be always forward biased, and the collector to the base junction should be always reverse biased. Okay, this is mandatory for the proper operation of a transistor, that is emitter base junction should be forward biased and the collector base junction should be reverse biased. So as you will know, because of the forward biasing, the resistance or the impedance offered by the emitter diode is small when compared to the resistance offered by the collector diode. That is because of the doping level. For when it is forward biased, the resistance is small. When it is reverse biased, the doping level is high. So now how this transistor working? So in order to proper operation of a transistor, we must have this condition, that is the voltage at the collector region should be greater than the voltage at the base, and it should be always greater than the emitter region. So what will happen is when you have uh, so in this case here we are having a few equations, that is we know that emitter will be always emitting electrons. So the electrons are starting from emitter, so it will be a current which is starting from emitter, and this current will enter into the base region. The electrons or holes, whatever it is, it will be entering in the base region, and because of the recombination, even though doping level is very small, there will be a slight amount of recombination at the base junction, and that will form a base current, and the remaining current which is coming from emitter will go to the collector region. So what we can easily say that the total current, that is sum of the base current and collector current, should be equal to the emitter current. So this is how we this is the basic equation of a transistor current. And so from this structure we can say that we can have equations. So this voltage at between the base and the ground is called VB. Okay, suppose there is a ground here, so this voltage is called VB, and this voltage between the base and the emitter is called VBE, and the voltage between emitter and the current is called VE. So we can write VBE is equal to VB minus VE. Or from this, if we consider this particular loop, okay, so here we can say VB is the applied voltage, that should be equal to the voltage between the base emitter junction plus the voltage across the emitter. So we can easily write VBE is equal to VB minus VE. And similarly, if we consider the other loop, so this loop here, our supply voltage, what is voltage between the collector and the ground, we will say that VC, this should be equal to the VCE plus VE. Okay, VCE is this voltage. Okay, so we can say VCE equal to VC minus VE. So these are the few equations here. In short, what we can do is just by changing the emitter current. Okay, if we are controlling the emitter current by some voltage, we can correspondingly change the current at the collector region. So basically, the transistor can be controlled simply by changing the base current. So this is the simple working of a transistor. Now, in order to have a proper operation of a transistor, we must have three connections. When you have an input and output, so we should have two terminals at the input and two terminals out the output. So there are three ways we can do this. We can either take base common for both input and output, or we can take emitter common for both input and output, or in the last case we can take collector common to both input and output. So here we'll consider the common base connection. So here the circuit diagram looks like this. Here you have emitter and the base will form the input part. Okay, So as we have told, the base emitter junction should be forward biased. Okay, forward bias. So in order to ensure the forward biasing, here we are giving a power supply. This VEE will ensure that the emitter based region is always forward biased. Now the output part here, the output part, this will form the output part. Here we are taking the collector and the base will form the output region. Okay, here this region is reverse biased. Here you can see this positive terminal is connected to the collector and negative terminal is connected to the base. So here we are using an NPN transistor, so this region is reverse biased. Okay, reverse biased, and this reverse biasing was ensured by the VCB power supply. Okay, and this power supply ensures that the outer collector base junction is reverse biased. Here another important parameter which we should understand is the current amplification factor. It is usually represented by alpha. So this alpha is written as IC by IV. That is the ratio of the output current, that is the collector current, change in the collector current divided by the change in the input current, that is delta IE, is called alpha. So this is called the current amplification factor. This is done by keeping the collector base junction constant. So just by keeping the collector base junction constant, we can evaluate alpha value. This is for the AC signal. When signal is applied, if the only DC signal is considered, we can simply say alpha is equal to IC by IE. Ratio of the collector current to the emitter current is the definition of alpha in the case of DC current. Now we have a common emitter connection, as in the case of base common base connection. Here emitter is taken common for both input and output. Here this VBE will ensure the base emitter junction is forward biased, and this VCC will ensure that collector base junction is reverse biased. So usually the voltage level, this is usually say, for example, it will have 2 voltage and this will be of the order of 10 to 12 volt. So this voltage levels will ensure that transistor's base emitter junction is forward biased and the collector base junction is reverse biased. Here the current amplification factor is given by beta, that is equal to delta IC by IB. Here the output current is this one IC and the input current is IB. So this delta IC by delta IB is denoted by beta. We know what is the value. Usually IC value is very high compared to IB. So this beta value can be of they say on the order of hundreds. It's more than hundreds. So alpha value is IC by IE, because IC and IE are almost equal and IC is always less than IE. So alpha value will be have a numerical value less than 1. Here beta will have a very high value. Now how do we establish a connection between beta and alpha? So here this beta is equal to alpha divided by 1 minus alpha. This we can easily derive. Beta is equal to IC by IB. Okay, for a DC value, for the time being I'm taking only DC value. So IC divided by IB can be written as IE minus IC. Okay, now we divide with the IC by IB, both denominator and numerator we divide with the IE, we divide with IE. So this become 1 minus IC by IE. So this IC by IE is nothing but alpha, and this is 1 minus alpha. So this is how alpha and beta are connected together. Now this is a common collector configuration. Again we have collector common for both input and output, and this expression for the current amplification factor is delta IE by IB, and this is denoted by gamma. So this gamma is similar way we can derive expression for gamma, that gamma is equal to 1 by 1 minus alpha. Okay, So you can try by yourself to establish this relation. And when we compare these three different configurations, uh, so the input resistance is common base configuration, it is very low, and for of the order of 100 ohm. But in the case of common emitter configuration, it is 750 ohm. But for collector junction, it is very high. And output resistance is very high in the case of common base, and moderately high of the order of 45 to 50 kilo ohm in the case of common emitter. And for common collector, it is very low value. And the voltage gain means the ratio of the output voltage to the input voltage. In the case of a common base connection, it is of the order of 150, and here it is 500, and this is less than 1. Okay. And what are the different applications for high frequency application? Common base is basically used for high frequency application, and common emitter is of the order is using in the case of audio frequency application. And the common collector configuration is usually used for impedance matching because of this property, because when we connecting a circuit with very high input impedance to a low input impedance, so if we can use this common collector configuration, we can easily connect a circuit with a high impedance to a region of low impedance. If we wanted to pass signal from this part to the this part, we can, in between, if we connect a common collector circuit, this impedance matching will not be a problem. Okay, this input resistance of common collector is high, so when we connect a high signal with the high impedance, can be easily connected to the common collector, and the output is having a low impedance, so we can easily uh, pass the signal to the outer part without any impedance mismatching. So these are the important comparisons of transistor connections. Now, in order to ensure that transistor is working properly, we should have we should know the exact values of the collector current and the various uh, collector emitter voltage. So IC and VCE are very important. So this value is very important for the proper operation of a transistor. So to establish the values of IC and VCE at different operating conditions, we must have a method called we must use a method called load line analysis. Here in the circuit, you can see, so if we consider the outer portion, VCC can be written as VCC is the supply voltage. This should be equal to the voltage across this resistance plus this voltage between these 2 points. Okay, so we can easily write VCE equal to VCC minus ICRC. So this will, for a fixed value of VCC and RC, this expression will form a straight line curve because we have only two variables. Okay, and this line is called the load line. So to find out the position of this straight line, we can easily um, establish the endpoints. So what is the endpoint? Suppose we consider IC equal to 0, that is along the x-axis. So IC equal to 0, we can easily say this VCE is equal to VCC. So in the output characteristics curve, if you are plotting between VC and IC by fixing different IB values, okay, by keeping the input current, base current constant, and we just vary the output voltage and current, we will get a curve like this. This is called output characteristics. Okay, so in the output characteristics, one endpoint will be this one. To get the other endpoint of the plot line, we will take the condition that VCE is equal to 0. So in that case, IC can be, from this equation, we can easily get IC equal to VCC by RC. So this VCC by RC will form the point A, and this VCC will form this straight line curve will give you the load line. And why this load line is important? Because in order to find out the operating point. These operating points are 0 signal IC and VC. Suppose I am not going to apply any signal. We are not applying no signal. So in that case, what is the current, DC current and the VC voltage existing at the transistor? So this is the operating point. With respect to this operating point, our signal will be varying. So this point is also called Q point. Okay, so this Q point is the value, the voltage or the characteristics curve uh, existing for a particular value of IB. Okay, characteristics value existing at a particular value of IB. So for a we will define the operating current IB. So we'll fix the IB value. Then in the IB value, you plot the lot line curve. The point of intersection of this lot line with the output characteristics curve will give you the Q point. Okay, this Q point, with respect to this Q point, our signal will be varying. So with respect to this point, the signal will be varying. That is why operating point is very important. So operating point should position exactly at the center of the output characteristics curve. Okay, if it is at extreme points, some signals may lost. We may lose some of the signals. So that is shown here. Suppose you are operating at this point. See cutoff point. So the point where the lot line intersect with IB is equal to 0 curve. So this is my IB is equal to 0 curve. So this is my output characteristics curve. That is a variation of IC versus VC by keeping IB 0. So if this point, all the point below this are called cutoff point. Okay, at cutoff point, the emitter diode and the collector diode are off. Both the diodes are off. Off means reverse bias. Okay, so both the regions are the voltage we are applying at the emitter and collector are in such a way that both regions are reverse biased. So if both regions are reverse biased, the transistor will not operate properly. So this region is called the cutoff region. Okay, and suppose at the other end, suppose in this point, our Q point is lying this point, which means the point where the lot line intersect with IB saturation. Maximum value of IB, so we're fixing this IB as IB sat. This is the maximum possible value. If this lot line is intersecting at this point, and if you are operating the transistor above this region, then it is called a saturation point. In saturation region, why is it happening? Because the at saturation point, both emitter and collector regions are on. That is, both are forward biased. Okay, so for proper operation of a transistor, you must operate it within this region. This region is called active region. So in the active region, the emitter diode is forward biased and the collector region is reverse biased. So this is called the active region. So there are three regions. The point, all the region below the IB equal to 0 curve will call cutoff region, and the region above saturation value of IB is called the saturation region, and this region where the operating point is lying at the midpoint of the output characteristics curve is called the active region. Now based on this idea, we will do some problems on transistor circuits. First question is, in a common base connection, the current amplification factor is 0.9. If the emitter current is 1 milliampere, what is the value of the base current? Okay, so this is the common base connection. The current amplification factor is given, that is equal to 0.9, and the emitter current is given. What you have to find out is the base current. Okay, so let us have this values. Alpha is equal to 0.9 because this alpha is given because of common base connection. നമുക്ക് തന്നിരിക്കുന്നത് കോമൺ ബേസ് കണക്ഷൻ ആയതുകൊണ്ട് കറണ്ട് ആംപ്ലിഫിക്കേഷൻ ഫാക്ടർ എന്നെ നമ്മൾ ആൽഫ എന്നാണ് റെപ്രസെന്റ് ചെയ്യുക. സോ ആൽഫ ഇസ് ഈക്വൽ 0.9. പിന്നെ നമുക്കറിയാവുന്ന കാര്യം എന്ന് പറയുന്നത് എമിറ്റർ കറണ്ട് ആണ്. സോ ദ എമിറ്റർ കറണ്ടിന്റെ വാല്യൂ എന്ന് പറയുന്നത് 1 മില്ലി ആംപിയർ. Okay, so what we wanted to find out is the base current. What is the value of the base current? Okay, so we know alpha is defined as alpha is equal to IC by IE is the definition of alpha. Okay, so here IC can be calculated as alpha IE. Okay, so this is alpha IE. So the alpha value is 0.9 and the IE value is 1 milliampere. Okay, so therefore IC is equal to 0.9 milliampere. Okay, 0.9 milliampere. So if we know IC and IE, the base current, the transistor basic equation നമുക്കറിയാം IB is equal to IE equal to IB plus IC. Okay, so IB is equal to IE minus IC. So that will be 1 minus 0.9 milliampere. So this is equal to 0.1 milliampere as the value of the base current. Okay, so if you know alpha value and IA, from there you can calculate IC. Using the IC value and IE value, IB can be calculated. This is a simple basic equation, and the second question is, in a common base connection, alpha is given. The voltage drop across the 2 kilo ohm resistor which is connected in the collector is 2 volt. Find the base current. Here let us draw the circuit diagram. For a common base connection, you have base, and then you have emitter, then you have collector. So in the collector, here we have the signal. Okay, and then you have the power supply. Then between the collector and the emitter base, you have another power supply, and then what is given is 2 kilo ohm resistance is connected at the output. So this value is 2 kilo ohm. Okay, and this is IC. Okay, and VCC and VBB. Okay, and the alpha value is given, that is 0.95, and what is given is the voltage drop across 2 kilo ohm resistance which is connected at the collector is 2 volt. So this is the resistance connected at the collector, and the voltage across this is given, that is equal to 2 volt. Okay, so what is given is the voltage across RC is 2 volt. Okay, suppose if you take IC as the collector current, then the voltage across RC is nothing but IC into RC. And this is equal to 2 volt. Here IC into RC value is given, that is 2 kilo ohm. 2 kilo ohm, that is equal to 2 volt. So from there IC is equal to 2 divided by 2 kilo, that is equal to 1 milliampere. Okay, so IC, we got IC. Now what the second part we can know, we can calculate is the IE value. നമുക്ക് ആൽഫയുടെ വാല്യൂ നമുക്കറിയാം. ആൽഫയുടെ വാല്യൂ ആൽഫയുടെ ഡെഫിനിഷൻ നമ്മൾ ഒരിക്കൽ കൂടെ പറയുന്നു. ആൽഫ ഇസ് എന്ന് പറഞ്ഞാണ് IC by IE. Okay, so using this one we can calculate IE. എങ്ങനെ calculate the IE is equal to IC by alpha. So IC is 1 milliampere and alpha is equal to 0.95. So this one calculating, നമുക്ക് എന്ത് കിട്ടും, ഈ വാല്യൂ എന്ന് പറയുന്നത് 1.05 milliampere. കാൽക്കുലേറ്റ് ചെയ്യുമ്പോൾ നമുക്ക് കിട്ടുക 1.05 milliampere. So IE value നമുക്ക് കിട്ടി 1.05 milliampere കിട്ടി. IC value നമ്മൾ ഓൾറെഡി കാൽക്കുലേറ്റ് ചെയ്ത് കഴിഞ്ഞു. ദാറ്റ് ഈസ് 1 milliampere. സോ നമ്മളോട് കണ്ടുപിടിക്കാൻ പറഞ്ഞിരിക്കുന്നത് ബേസ് കറണ്ട് ആണ്. സോ you can easily calculate base current as IE minus IC, that is equal to 0.05 milliampere, or usually base current നമ്മൾ സാധാരണ മൈക്രോ ആംബിയറിന്റെ ടേംസിലാണ് പറയുക. സോ അങ്ങനെയാണെങ്കിൽ this is equal to 50 micro ampere is the base current. So this is how we solve a problem like this. Now for a common base circuit in the figure, determine IC and VCB. Assume the transistor is in silicon transistor. Okay, so now I will draw the circuit diagram that is given along the question. That is this is 8 volts, this is 18 volt, and this resistance value is 1.2 kilo ohm. Okay, so these are the parameters given. VBB is equal to 8 volt, and this is VCC equal to 18 volt, and this RC equal to 1.2 kilo ohm, and here RB is equal to 1.5 kilo ohm. So what you have to calculate is IC and VCB. So for that, let us consider the input section. So we'll consider this input section. Okay, so this part only. Okay, this part. So we will calculate, we will use the Kirchhoff's law, KVL, Kirchhoff's voltage law. So the supply voltage is VBB, and this is VBB, and this VBB should be equal to the voltage across this voltage, and since there is no resistance here, there won't be any voltage at the base region. So this is not RB, this is E. So IE RE. Okay, this voltage across R plus VBE. VBE is the voltage between the base and the emitter junction. Okay, since it is a silicon transistor, for a silicon transistor VBE value is equal to 0.7. So this is equal to IE into 1.5K plus 0.7, and this is equal to 8. So IE is equal to 8 minus 0.7 divided by 1.5K, and calculating this one, what you will get is 4.87 milliamp. Okay, so IE is equal to 4.87 milliampere. Now what we need is VCB, collector base voltage. Okay, here VCC, if we consider the output part, VCC supply voltage, that should be equal to the voltage across resistance, this RC. Okay, so that is IC into RC, current into resistance, plus um, VCB. VCB is the voltage between the this region, VCB. Okay, so VCB is equal to VCC minus ICRC. VCC equal to 18 and IC is equal to 4.87. We will assume that IC equal to IE because it is almost equal 1.2K. So this become, on calculating you will get this value is equal to 12.16 volt. So IE is approximately equal to IC, that is equal to 4.87 milliampere, and VCB is equal to 12.16 volt is the value of IC and VCB. Next, for a transistor, beta is equal to 45 and the voltage drop across 1 kilo ohm which is connected in the collector circuit is equal to 1 volt. Find the base current for the common emitter connection. Okay, so let us draw the circuit diagram. This is a common emitter connection. So in the case of a common emitter connection, our circuit diagram looks like this. This is 1 kilo and this voltage is given, that is 1 volt. So here the voltage drop across 1 kilo ohm resistance is equal to 1 volt. So which means IC into RC equal to 1 volt. So IC is equal to 1 divided by 1K, that is equal to 1 milliampere. Okay, so here what is given is beta. Beta is given, that is equal to 45. We know beta is equal to IC by IB. So IB is equal to IC by beta. That is 1 by 45 milliampere. So that is equal to 0.022 milliampere, and this is nothing but 22 microampere. This is how we calculate the base current in the case of a common emitter connection. Now a transistor is connected in common emitter configuration in which the collector supply voltage is 8 volt and the collector voltage drop across the resistance RC connected in the collector circuit is 0.5 volt. The value of RC is given and alpha is given, the value of the collector emitter voltage and the base current. So let us draw the circuit diagram once again. So what is collector supply voltage is 8 volt, so that is 8 volt. Then voltage drop across the RC connected at the collector is equal to 0.5 volt, so this is 0.5 volt. Okay, and this is RC and the RC value is 800 ohm, so here RC equal to 800 ohm and IC into RC is equal to 0.5 volt. Okay, So from there you can calculate RC, that is IC equal to 0.5 divided by 800, that is equal to 0.625 milliampere. IC value is equal to 0.625 milliampere. Now alpha is given here, alpha is equal to 0.96. So from there we have to get the beta value. So the relation between beta and alpha are calculated previously. Alpha divided by 1 minus alpha is the value of beta. So this is 0.96 divided by 1 minus 0.96. So that value will be equal to 24. So beta is given. So we calculated beta. We got IC value is equal to 0.625 milliampere. Okay. And beta value we got it as 24. ഓക്കെ, ഇത് രണ്ടും കിട്ടിക്കഴിഞ്ഞാൽ പിന്നെ നമുക്ക് ഈസി ആയിട്ട് കാൽക്കുലേറ്റ് ചെയ്യാം. നമ്മൾ കണ്ടുപിടിക്കാൻ പറഞ്ഞിരിക്കുന്നത് ബേസ് കറണ്ടും collector emitter voltage on. So first we'll calculate the base current. So IB equal to IC by beta. Okay, so that is 0.625 divided by 24, and that is equal to 0.026 milliampere. So that is equal to 26 microampere. So IB കിട്ടി. IB 26 microampere നമുക്ക് കാൽക്കുലേറ്റ് ചെയ്തു. ഇനി നമുക്ക് കാൽക്കുലേറ്റ് ചെയ്തത് കളക്ടർ എമിറ്റർ വോൾട്ടേജ് ആണ്. കളക്ടർ എമിറ്റർ വോൾട്ടേജ് എന്ന് പറഞ്ഞാൽ ഇതാണ് കളക്ടർ എമിറ്റർ വോൾട്ടേജ്. കളക്ടറിനോ എമിറ്ററിനോ ക്രോസ് ആയിട്ടുള്ള വോൾട്ടേജ്. ഇവിടെ അഗൈൻ നമ്മൾ കിർച്ചോഫ്സ് ലോ ഈ സെക്കൻഡ് പാർട്ടിൽ അപ്ലൈ ചെയ്ത് കഴിഞ്ഞാൽ എന്ത് കിട്ടും? ഇവിടാണ് നമ്മൾ കിർച്ചോഫ്സ് ലോ അപ്ലൈ ചെയ്യേണ്ടത്. സോ അവിടെ VCC is a supply voltage that should be equal to ICRC plus VCE. So VCE will be equal to VCC minus ICRC. Okay, so ICRC യുടെ വാല്യൂ നമുക്ക് തന്നിട്ടുണ്ട്, that is equal to this 0.5 volt. So this is VCC equal to 8, ICRC is 0.5, so that is equal to 7.5 volt. So our answer to this question is 7.5 volt and 26 microampere. This is how we calculate such a problem. Now next question is to draw the load line, DC load line of the circuit shown in the figure. So now let me draw the circuit. The circuit is a common emitter configuration. Sorry, this is 2.5K and VCC is this is incorrect. Okay, let me erase this one. Erase this one. This is 2.5K and this VCC is equal to 12.5 volt. This is 12.5 volt and okay, and this is IB. I see. Okay, so this is the circuit diagram. So you have to draw the load line. So in order to do that one, let us consider the uh, output loop. Okay, this one. So in this output loop, our equation is VCC equal to the supply voltage, this VCC is equal to the voltage across this one collector and the emitter, that is VCE, plus the voltage across the collector load resistance, that is IC into RC, current IC into RC. So to draw the dot line, we must consider that first two cases. One is let IC equal to 0. So if IC is equal to 0, VCE will be equal to VCC. Okay, and for the, so we got one point, that is VCC and 0. So here VCC is equal to 12.5. So 1.0. So this point A uh, is given by 12.50 volt. Now to get the point B, let VCE equal to 0. So here in this equation, so VCE is equal to 0 means IC equal to VCC by RC. Okay, VCC is equal to 12.5 and divided by 2.5K, that will be equal to 5 milliampere. So the point B is given by 0 and 5 milliampere. So our load line will be a curve on the output characteristics line. So here x-axis is given by VCE and the y-axis is given by IC. So the point number A will be is this one. Take this one. So this is A, 12.5 and 0, and the point B is this one, this 0, 5. So this will be a straight line. So this is the uh, DC load line for this circuit. Okay, so this is the way, this is how we approach the DC load line problems. Next, in the circuit given, the VCC is equal to 12 volt and RC, this is RC equal to 12 volt, this is VCC equal to 12 volt and RC equal to 6 kilo ohm. What is the Q point if the zero signal base current is 20 micro ohm and beta is equal to 50? So what is given as VCC equal to 12 volt and RC is given, that is equal to 6 kilo ohm, and our IB is given 20 micro ampere and beta equal to 50. This much data is given. From this we have to get the Q point. What is the Q point? So our circuit, let me draw the circuit. So a circuit is again a common emitter circuit. Here no signal, we are not giving any signal because we are discussing only the DC dot line case. Six kilo ohm as the RC and VCC equal to 12 volt, and so this is the data given. So from there we have to find out the load line. So it's relatively very simple, straightforward thing. Or VCC, again our expression is equal to VCC is equal to VCE plus IC RC. Okay, so when VCE is equal to 0 or IC equal to VCC by RC, so VCC is equal to 12 volt, RC equal to 6K, this will give you 2 milliampere. Okay, IC is equal to 2 milliampere. Now once you get the IC, um, our VCE will be now in this equation when IC equal to 0, so VCE will be equal to VCC equal to full volt. Okay, so our lot line will be uh, a straight line. This IC, and this is VCE, and this straight line is this one. Okay, so this point is 12 volt 0, and this is 0, 2 milliampere. Now to get the um, correct zero signal Q point, to find the Q point, what is we have to use these expressions. IB equal to 20 microampere is the zero signal IB, and beta is equal to 50. From there we can calculate our IC value. So IC equal to beta IB, so that is equal to 50 into 20 microampere, that is equal to 1 milliampere. Okay, 50,000 microampere, that will be equal to 1 milliampere. So this is equal to 1 milliampere. So from there we can, if the actual IC value passing through the circuit is given, so that is equal to 1 milliampere. So in this equation, if we put IC value, you will get corresponding VCE value. So in this equation, if VCE equal to VCC minus IC RC, so this is equal to 12 minus IC is equal to 1 and RC equal to 6. So again this is equal to 6 volt. Okay, so our correct operating point is actually VC equal to 6 volt and IC equal to 1 milliampere. So in this curve, if you draw curve like this is corresponding to IB is equal to 20 microampere, and this point of intersection is actually our Q point, and that Q point value is given by 6 and 1 milliampere, 6 volt and 1 milliampere. So the answer is 6 volt and 1 milliampere are the corresponding Q point in the question. Now again determine the Q point. Next question, determine the Q point of the transistor circuit shown, and here beta is given and VB is equal to 0.7. So beta, only thing given is beta is equal to 200 and VBE equal to 0.7 volt, which means it is a silicon transistor, and our circuit is like this. This is equal to so this is 10 volt, input voltage is 10 volt, and here is one resistance, so that I forget, this is 46.5 kilo ohm, 46.5 kilo ohm, and this is 200 ohm. This voltage is 20 volt. Okay, so so since other things are not given, you have to use the input loop here in the circuit. So input loop, this is my VBB. So VBB equal to IB into RB plus VBE. Okay, so this voltage is equal to the voltage across this resistance plus VBE. Okay, so from there I can calculate IB, that is VBE is 10 and VBB is 10, VBE is equal to 0.7, and this RB value is equal to 46.5, and this will be equal to 20 micro 46 kilo ohm micro ampere. Okay, so IB is equal to 200 sorry 20 micro ampere. So from there, using the beta value, we can calculate IC equal to beta IB. Okay, and beta value is equal to 200 into 20 micro ampere, and this 200 into 20 micro ampere will give you a value equal to 40 milliampere. Okay, so IC equal to 40 milliampere. To this is the actual value of IC which is passing through the circuit when we are not applying any AC signal. This is so we have to calculate the corresponding VCE value. So VCC equal to VCE plus IC RC. So VCE will be equal to ICR. VCC is equal to 20 and IC equal to 40 milli into RC equal to 200. So this 20 minus this value is equal to on calculating you will get this value equal to 12 volt. Okay, so this is equal to 8. So our VCE equal to correct value of VCE is 12 volt and IC equal to 40 milliampere is the point of the circuit. Okay, so then the next question is to find the Q point of the transistor circuit. Now here beta is given, VB is given. Okay, so what is given is beta and VBE. VBE is equal to 0.7. Now and our circuit is like this. This is 47K. This is grounded. So 47K, and you have another resistance. This is 4.7K, and this voltage is equal to minus VEE, and that value is equal to minus 10 volt. And see, this is 1 kilo ohm, and it is connected to a 10 volt power supply. So this is the circuit. So here you have an emitter resistance connected to minus potential of 10 volt, and then and for 47K resistance at the base, and a 1K resistance at the RC, the collector side, and then a plus 10 volt VCC. So we have to get the Q point. That means you have to calculate VCE and IC of the circuit corresponding to these conditions. Okay, ഇനി നമുക്ക് ചെയ്യാൻ പറ്റുന്ന കാര്യം എന്താണെന്ന് വെച്ചാൽ നമ്മൾ ഇൻപുട്ട് സർക്യൂട്ടറി എടുക്കുക. So we'll discuss the input circuitry first. So here our VEE is equal to VEE is equal to the voltage across this one plus VBE plus this voltage. So sum of the three voltages. So supply voltage is equal to IB RB, okay, plus VBE base emitter voltage plus the voltage across the emitter resistance, that is IE into RI. Okay. Okay, so you have to obtain the value of IB or IE from this equation. So what is given is beta. So we know that IC is equal to beta IB. Okay, and we will assume that IC is almost equal to IE, that is equal to beta. Okay, IC equal to IB, and so instead of IB, we can substitute IB is equal to IE by beta. Okay, so we'll substitute this one in this equation, so that our VEE is equal to IE by beta into RB plus VBE plus IE into RE. Now the values are IE by beta is equal to 100. Okay, and RB is equal to 47K plus 0.7 plus IE into 4.7K. So this is equal to IE, you will take common 47 into 47K by 100 plus 4.7K plus 0.7. So VEE is equal to 10 volt. So you can calculate IE is equal to 10 minus 0.7 divided by 47K by 100 plus 4.7K. So this is equal to 9.3 divided by 5.17K. We will calculate this is equal to 5.17K, and this value is equal to 1.8 milliampere. Okay, so once you get this expression, we can use the other equation VCC. You will use the output loop. So VCC equal to ICRC plus this voltage VCE. Okay, VCE plus the emitter resistance, emitter voltage IE into R. So this is equal to, so VCE equal to VCC minus IC into RC plus RE. Again we are taking IC is approximately equal to IE. So combining this one and taking to the left hand side. So this is 10. Okay, and one more thing here, you have to include this minus potential also. So this is equal to minus VEE. So this minus V, when we go to the other side, it becomes plus VE. Okay, so this is 10 minus IC is 1.8 plus 4.7 plus 1 kilo plus 10. So this is equal to 20 minus 1.8 into 4.7 plus 1. That value is equal to on calculating, this value will be equal to 9.74 volt. So your Q point of the circuit is 9.74 volt, and IC value is corresponding to IC value is 1.8 milliamp. And this is the answer to the problem. So it's we have to include, when a minus VE comes in the circuit, you have to include that one in the output loop. Okay, സാധാരണ നമ്മൾ എഴുതുമ്പോൾ VCC equal to ICRC plus VCE plus IER മാത്രമേ ഉള്ളൂ. പക്ഷെ ഇവിടെ നെഗറ്റീവ് പൊട്ടൻഷ്യൽ തന്നിരിക്കുന്നുണ്ട്. ഈ നെഗറ്റീവ് പൊട്ടൻഷ്യലും ഈ സർക്യൂട്ടിലേക്ക് നമ്മൾ ഉൾപ്പെടുത്തണം. അക്കാര്യം ശ്രദ്ധിക്കണം. In this problem, the question is to find the voltage gain or voltage amplification. So here our transistor is a common base transistor amplifier, and it has an input resistance is equal to 20 ohm, and the output resistance is 100 kilo ohm. The collector load is 1 kilo ohm, and if this input signal is 500 millivolt is applied between the emitter and the base, find the voltage amplification. Assume alpha is equal to 1. So this is again a common base configuration circuit. Okay, so here what the things given are input resistance. So Ri തന്നിട്ടുണ്ട് 20 ohm. Okay, and output resistance തന്നിട്ടുണ്ട്. Output resistance is equal to 100 kilo ohm. Okay, and load resistance, collector load തന്നിട്ടുണ്ട്. Collector RC is equal to 1 kilo ohm, and input voltage തന്നിട്ടുണ്ട് 500 millivolt. Okay, so what we wanted to find out is the voltage gain or voltage amplification. Okay, voltage amplification means the ratio of output voltage to the input voltage. Okay, so we have to find out both input voltage. Input voltage is 500 millivolt. So we have to find out the output voltage. To find out the output voltage, we need to get the IC and IC value. Okay, what is IC? So output voltage is actually it is a common base configuration. So in the case of a common base configuration, so you have the signal here. ഇവിടെയാണ് നമ്മൾ സിഗ്നൽ കൊടുത്തിട്ടുണ്ട്, and this is my collector. So this is biased. Then okay, and you have the output load is given. Okay, this is 100k, and the input resistance is 20 ohm. Okay, so from this what we want is to find out the output voltage VO. Okay, so VO is, in this case, it is IC into RC. Okay, so we have to find out IC first. So to find out IC, we have to find out IE. We have to get the IE value. This is the emitter current. Okay, so this is the emitter current IE. So the emitter current can be obtained by taking the input voltage to the input resistance. Okay, so input voltage is given as 500 millivolt. Okay, and the input resistance is 20 ohm. So this is equal to, so on calculation you will get this is equal to 25 milliampere current. Okay, IE is given. So IE we got IC. IE യുടെ വാല്യൂ നമ്മൾ കണ്ടുപിടിച്ചു. ഇനി നമുക്ക് തന്നിരിക്കുന്നത് ആൽഫയുടെ വാല്യൂ നമുക്കറിയാം. Alpha is almost equal to 1, which means alpha equal to IC by IE, and that is equal to 1, which means IC equal to IE. Okay, so we can assume that IC equal to IE. So output voltage is equal to IC RC. ഇതെന്ന് പറയുന്നത് IC എന്ന് പറയുന്നത് 25 into RC is equal to 1k. So this is 1k. So this is 1k. Okay, so this is equal to 1k. So that is equal to 25 volt. Okay, output voltage is 25 volt. So what we want is the gain. Voltage gain is equal to VO by Vin. Okay, VO is equal to 25 and Vin is equal to 20 millivolt. Okay, so this one calculation, input is 500 millivolt. Sorry, it is 500 millivolt. Okay, 500 millivolt. On calculation you will get this value is equal to 50. So the gain of the circuit is equal to 50 is the correct answer. Next question. A base current of 50 microampere is applied to the transistor in the figure, and a voltage of 5 volt is dropped across RC. Calculate the alpha for the transistor. So the circuit diagram, let me draw the circuit diagram. So we have a common emitter circuit diagram is given in the question. Okay, and you have resistance. This is 100k, Okay, and this is 1K, and what is given is 5 volt is dropped across the circuit. Okay, so here 5 volt is dropped across the 1K resistance. So which means the things given are base current തന്നിട്ടുണ്ട്, that is 50 microampere. Okay, and a voltage drop of VC equal to ICRC is given, that is equal to 5 volt. Okay, ആർ സിയുടെ വാല്യൂ നമുക്കറിയാം, ആർ സി ഈക്വൽ ടു 1 കിലോ ഓം. ആർ സി അറിയാമെങ്കിൽ അവിടെ നമുക്ക് ഐ സി കണ്ടുപിടിക്കാം. ഐ സി ഈക്വൽ ടു 5 ഡിവൈഡഡ് ബൈ 1K, that is equal to 5 milliampere current. Okay, IC is given, so IC is given, that is equal to 5 milliampere, and IB is equal to 50 microampere. So the microampere is nothing but 50 into 10 raised to minus 3 milliampere. Okay, so that is nothing but 0.05 milliampere. Okay, that is IB. So using these two നമുക്ക് I കണ്ടുപിടിക്കാം. I നമുക്കറിയാം, I equal to IC plus IB. Okay, so IC value എന്ന് പറയുന്നത് 5 ആണ്, IB എന്ന് പറയുന്നത് 0.05 ആണ്. So total is equal to 5.05 milliampere. സോ നമ്മളോട് ക്വസ്റ്റ്യൻ ചോദിച്ചിരിക്കുന്നത് ആൽഫ കണ്ടുപിടിക്കാനാണ്. ആൽഫ നമുക്കറിയാം, ആൽഫ ഈസ് ഈക്വൽ ടു ഐ സി ബൈ ഐ ഇ. ഓക്കെ, ഐ സിയുടെ വാല്യൂ 5, ഐയുടെ വാല്യൂ 5.05. സോ ഓൺ ടേക്കിംഗ് ദിസ് വാല്യൂ കാൽക്കുലേറ്റ് ചെയ്യുമ്പോൾ നമുക്ക് കിട്ടുന്ന വാല്യൂ ഇറ്റ് ഈസ് ഈക്വൽ ടു 0.99. So this is the alpha value for this particular circuit. In this question, for BJT, the current amplification factor alpha is equal to 0.9. This transistor is connected in common emitter configurations. When the base current is changed by 0.4 milliampere, the change in the collector current will be dash in milliampere. So we have to calculate this in milliampere. So what the question is, alpha is given, okay, 0.9. Okay, so here a common emitter configuration. So delta B is given, change in the base current തന്നിട്ടുണ്ട്, that is equal to 0.4 milliampere. So what is the corresponding change in the IC value? Delta IC യുടെ വാല്യൂ എത്രയാണെന്നുള്ളതാണ് നമുക്ക് കണ്ടുപിടിക്കേണ്ടത്. സോ ഇത് നമുക്ക് കണ്ടുപിടിക്കണമെങ്കിൽ നമുക്ക് എന്ത് വേണം? We have to connect between IC and IB. So that can be done by B. Consider calculating the beta value. Beta value കിട്ടണം. So alpha നമുക്കറിയാമെങ്കിൽ beta നമുക്ക് കണ്ടുപിടിക്കാം. Beta is equal to alpha divided by 1 minus alpha. Okay, that is 0.9 divided by 1 minus 0.9, that is equal to 0.9 by 0.1, that is equal to 9. Beta value എന്ന് പറയുന്നത് 9 ആണ് in this case. So നമുക്ക് beta is actually defined as, in the case of an AC current, it is delta IC by delta IB. Change in the base current divided by change in the collector current divided by the change in the base current is the expression for beta. So delta IC is equal to beta into delta IB. So beta is 9 and delta IB is 0.4. So this one multiplying it becomes 3.6 milliampere. So change in the collector current is equal to 3.6 milliampere. For a change of delta B of 0.4 milliampere, creates a delta IC value equal to 3.6 milliampere. In this question, we have to calculate the output resistance. If the collector current changes from 2 milliampere to 3 milliampere in a transistor, when a collector emitter voltage is increased from 2 volt to 10 volt, what is the output resistance? So here we have to calculate the output resistance. So output resistance RO is equal to delta VO by delta IO. In fact, it is the common emitter configuration. So for a common emitter, output current is IC. So delta VO by delta IC. So here delta VO is given, that is 10 minus 2, and delta IC is given 3 minus 1 to 2, that is 8 divided by 1, that is equal to 8 kilo ohm. Because this is in milliampere. So this is RO value is equal to 8 kilo ohm. It's direct simple calculation. And next question, change of 200 millivolt in the base emitter voltage causes a change of 100 microampere in the base current. Find the input resistance. Again, it is very straightforward question. So the input resistance Ri is equal to delta V in by delta I B. Okay, common emitter configuration once again. So delta V in is change in the V in means actually delta voltage between the base and the emitter divided by delta IB. So this delta VB is given, that is 200 millivolt divided by 100 microampere. So this is equal to 2 10 raised to minus 3 in the denominator. This 200 will go, that is 10 raised to minus 6. So that is equal to 2 into 10 raised to 3, and we take this one up, that is equal to 2 kilo ohm. Okay, now a silicon transistor with a built-in voltage of 0.7 volt is used in the circuit with VBB is equal to 9.7 volt, RB is equal to 300K, and VCC equal to 12 volt, and RC equal to 2 kilo ohm. Which of the following figure correctly represents the load line and the Q point? So in this question, the circuit diagram is a common emitter configuration circuit. Okay, and here we have a resistance, and here we have a potential, and here we have RC value and then another potential. Okay, so this RC is equal to 2 kilo ohm, and VCC equal to 12 volt, VBE is equal to 9.7 volt, and this is 300 kilo ohm. Okay, so this is a silicon transistor. We can assume this is VBE equal to 0.7 volt. Okay, now we have to calculate the load DC load line and then the Q point. So first we will calculate the load line expression. We know VCE equal to VCC minus ICRC. Okay, VCC equal to ICRC plus VCE. Okay, so for IC equal to 0, VCE equal to VCC, that is equal to 12. Okay, and then for VCE equal to 0, IC equal to VCC by RC. So 12 divided by 2, that is equal to 6 milliampere. So our load line will be a line connecting 12, 0 and 0, 6. Okay, now which is the Q point? So load line will be a line connecting 6 to 12. These two, so these two are eliminated. Okay, so these two are the correct. Now we have to find out where is the Q point. in order to Q point കണ്ടുപിടിക്കാൻ വേണ്ടി നമ്മൾ എന്ത് വേണം, ഓപ്പറേറ്റിംഗ് ഐ ബി എത്രയാണെന്ന് കണ്ടുപിടിക്കണം. ഇവിടെ 2 IB 3 IB തന്നിട്ടുണ്ട്. അതിൽ ഏത് IB ആണ് കറക്റ്റ് ആയിട്ടുള്ള IB എന്ന് കണ്ടുപിടിക്കണം. അത് കണ്ടുപിടിക്കണമെങ്കിൽ നമ്മൾ ഇൻപുട്ട് ലൂപ്പ് എടുക്കണം. സോ വി വിൽ ടേക്ക് ദിസ് ഇൻപുട്ട് ലൂപ്പ്. സോ VBB is equal to voltage across this resistance, that is IB into RB plus VBE. So this is 9.7 equal to IB into 300K plus 0.7. So IB is equal to 9.7 minus 0.7 divided by 300K, that is equal to 9 divided by 300K, that is equal to 30 microampere. So our operating base current എന്ന് പറയുന്നത് 300 microampere ആണ്. So sorry 30 microampere ആണ്. So the Q point എന്ന് പറയുന്നത് it is a intersection between the operating base current and the load line. So this is the Q point. So the correct answer is B. It's the correct answer. Okay, thank you.